In today's lab experiment, we're going to investigate the relationship between pressure and the temperature of a gas in a container. We're going to vary the temperature and observe the pressure, so the temperature is the independent variable in our experiment and the pressure is the dependent variable. If you've ever seen a balloon left outside on a cold night, you know that the volume of a gas is related to the temperature, so we'll have to control for volume. This is pretty easy to do if we use a rigid container that doesn't change its volume. In our experiment, we'll use a glass flask. If you've ever pumped up a tire, you know that changing the number of particles of air in the tire has an effect on the pressure. So we'll also have to control for this variable by making sure that the number of particles doesn't change when we measure the pressure. This is also pretty easy to do if we just make sure that the flask stays sealed during the experiment. We're going to be using a pressure sensor that can be read by a computer with the help of a special lab interface. The sensor will be attached to our flask so it can measure the pressure of the gas inside by having a hose poked through a stopper that's sealed on to the top of the flask. We'll also be using a temperature probe that can be read through the same lab interface to measure the temperature of the gas, and we'll vary the temperature by using a hot plate. The gas we'll be using in this experiment is the one that's easiest to find, air. Here's how we'll gather our data. First, we'll trap gas inside the flask by just plugging the top with the rubber stopper that has the pressure sensor poked through it. We'll put some ice and water in a large beaker and let it chill until the water is good and cold. Then we'll remove most of the ice to get it out of our way. Then we'll put the beaker on a hot plate that we haven't turned on yet, and we're ready to begin. We'll put the flask in the water and make sure that most of the flask is immersed in water the whole entire time. We'll put our temperature sensor in the water as well and make sure that its tip is pretty close to the flask at all times. We're doing this because we can't really put the flask on the hot plate directly and heat it up because it would probably crack. So we're going to use what's called a water bath to regulate the temperature of the gas inside. We'll put the flask in the water and make sure that most of the flask is immersed in water the whole entire time. And we'll set up the data collecting unit so it measures the pressure and the temperature every 30 seconds for as much time as we have. As soon as we reach our first data point, we'll turn on the hot plate to a medium-high setting and gather data until the water boils, or as much time as we have. To keep from getting hot and cold spots in the water, we'll keep swirling the water around with the temperature probe. When I did this experiment by gathering data for about 30 minutes from a temperature that started at 4 degrees C and ended up at 56 degrees C, I got this result. Let's analyze it. The fact that the correlation number on the linear fit is close to 1 tells me that a line is a good model for this relationship. Now, if pressure is caused by the collisions of particles with the pressure sensor, and if particles slow down when the temperature gets lower, it would make sense that there should be no pressure when the temperature is as low as it can be, because that would mean that the particles aren't moving at all, so they can't collide with anything. However, we have a vertical intercept that's not exactly zero. Is it reasonable to throw it out? The general rule is that if your vertical intercept is less than 5% of the largest value on the vertical axis, you can throw it out if it makes logical sense to do that. The highest value of pressure is about 820 torr. 5% of that is about 41 torr. Our vertical intercept is way more than 41 torr, so it's not reasonable to round to zero. Now, scientists knew there was something wrong with this situation, and they quickly realized that the problem is 0 degrees C is not actually zero temperature. As everyone who lives where we live knows, in the north, it's totally possible for the temperature to be negative. So the temperature where the particles have actually stopped moving, which would be the coldest possible temperature, isn't really 0 degrees C, it's some negative temperature. Now, we could just leave the vertical intercept there, but because it's a hassle to deal with a vertical intercept, in our model, scientists were interested in finding out what is the coldest temperature possible and then making a new temperature scale that starts there. Now, we can do this by just expanding the graph and finding what temperature it is when the pressure actually reaches zero. That's what we'd call the horizontal intercept. You can see from this graph that that's about 270 degrees below zero. You can see that that line that comes from our data, when it extends down, crosses at, it looks like about 270 below zero. If you do this very carefully, as scientists have done over the years many, many times, and kind of take an average of what they find with experiments like this, that temperature, which we call absolute zero, is more precisely 273.15 degrees C below zero. So they created a new temperature scale. It's called the Kelvin scale. It's named after a famous scientist. A degree on the Kelvin scale is the same exact size as a degree Celsius. It just starts at absolute zero. So there are no negative temperatures. So to convert any temperature from Celsius to Kelvin, you just add 273 to it. 273.15 to be more precise, but 273 is close enough. So for example, 0 Celsius would be 273 kelvins. 100 Celsius, the boiling point of water, would be 373 kelvins. The actual slope of this line is specific to our particular temperature and our particular volume, our particular number of particles. So it's probably not useful for predicting the behavior of any other system besides the one that we have. But we can make a conclusion. The pressure is directly related to the temperature. In other words, the relationship between pressure and temperature is a straight line. And if we use Kelvin temperature, absolute temperature, there's no vertical intercept. So we could say pressure is equal to a constant number times temperature. And that's a good model for how pressure is affected by temperature. If we divide both sides by temperature, we get this same result, but in a probably more useful form. The ratio of pressure to temperature is a number that never changes, a constant temperature. So as long as we're using absolute temperature, what this means is whatever happens to temperature, the same thing has to happen to pressure. So if you double the absolute temperature, the pressure also has to double. If you cut the absolute temperature in half, the pressure also has to be cut in half. Now it's very important to remember that this only works if you're using absolute temperature, like kelvins. So if the temperature goes from 25 degrees C to 50 degrees C, that might seem like it's doubling, but it actually isn't, because 25 degrees C is 298 kelvins, and then if you add 25 to that, you're at about 300 and something in kelvins, and that's actually not a doubling. So it's very important to remember that if you're using this relationship in this way, you have to use Kelvin temperature. So that's our conclusion. Whatever happens to the absolute temperature, the exact same thing has to happen to the pressure, because that ratio remains constant.